Candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. Measuring length. In physics experiments, when we need to measure the length of an object, it is important to select a suitable instrument for the task. Different instruments offer varying degrees of precision to suit the object's size. Lengths exceeding 100 centimeters. We can be used the measuring tape. Its precision is 0.1 centimeters. For example, it is used to measure the waistline of a person or the dimensions of a room. Lengths between 5 and 100 centimeters. We can be used the meter rule or ruler. Its precision is 0.1 centimeters. For example, it is used to measure the length of an object as pencils or wires. Lengths between 1 and 10 centimeters. We can be used the vernier caliper. Its precision is 0.01 centimeters. For example, it is used to measure the diameter of a beaker, sphere or cylinder. Lengths less than 2 centimeters. We can be used the micrometer. Its precision is 0.001 centimeters. For example, it is used to measure the thickness of a wire, paper or thin sheet of material. Zero error. Zero error is caused by faulty equipment that doesn't reset to zero properly. Zero error is simply the reading of the measuring device when input quantities are zero. For example, a stopwatch that has not been reset to zero before use can give a zero error. To minimize zero error, it's important to calibrate your instrument before use. Calibration ensures the instrument's readings are accurate and consistent. Parallax error. Parallax errors can occur during measurement. For example, incorrect positioning of the eye. This is wrong position of the eye. This is wrong position of the eye. This is right position of the eye. We should read the scale at perpendicular angle to the scale for avoiding the parallax error. The object is not touching the marking of the scale. This is wrong. This is wrong. This is right for the measuring tape, meter rule and ruler. Ensure that the object is in contact with the scale. More measurement techniques in and small length. Measure the diameter of a ball bearing. We can use the two wooden blocks to make it easier to measure the diameter of 4 ball bearing as shown. The blocks mark the edges of the first and last ball bearings. So, the total diameter is 9.3 minus 3 is equal to 6.3 centimeters. Divide the total by the number of ball bearings. So, diameter equals 6.3 to divide by 4 is equal to 1.6 centimeters. Measure the thickness of one paper. Using a ruler. Measure the thickness of 500 sheets of paper using a ruler. Divide the thickness of 500 sheets by 500 to get the thickness of one sheet. Repeat the reading at different positions of thickness of 500 sheets of papers and find the average. Using the micrometer screw. Check the zero error of the micrometer. Measure the thickness of 20 sheets of paper using the micrometer. Divide the thickness of 20 sheets by 20 to get the thickness of one paper. Repeat the reading of 20 sheets thickness at different positions of 20 papers and find the average. Measure the volume of an object using the measuring cylinder. Fill the measuring cylinder with water. Read the initial volume, V1, by viewing the scale at perpendicular angle at the bottom of the meniscus as shown. Carefully place the object into the water. The water level rise as shown. Read the final volume, V2, by viewing the scale at a perpendicular angle at the bottom of the meniscus. The volume of the object is the final volume, V2, minus the initial volume, V1. Measure the time period of a pendulum. The time period of a pendulum is the time taken for the pendulum to complete one oscillation. One oscillation is from A to B and back to A. Place the pin at here as the fiducial mark for counting the number of oscillations. Set a stopwatch at 0. Measure the time taken of a ball to complete n oscillations with a stopwatch, and n should be about 10 to 20 oscillations. In this experiment, n equals 10 oscillations. Divide the time taken of n oscillations by n to get the period of the pendulum. For this example, the period is 16.0 to divide by 10, which equals to 1.6 seconds. Repeat the reading at least 3 times and find the average of the period to get the accurate value. Physical quantities. There are 2 types of physical quantities as scalar and vector. All physical quantities consist of a numerical magnitude and a unit. For example, the volume of 150 cubic meters. The volume is the physical quantity. It is a scalar quantity, because the volume has no the direction. The value of 150 represents the numerical magnitude, or size of the volume. The cubic meters represents the unit of volume. The weight of 500 newtons. The weight is physical quantity. It is a vector quantity, because it has both magnitude and direction. The value of 500 represents the numerical magnitude, or size of the weight. The newton is the unit of weight. The direction of weight is always downward. Scalar and vector. A scalar quantity has only magnitude, or size, which is a numerical value. A vector quantity has both magnitude and direction. For example, some scalar quantities in physics include distance, speed, time, mass, energy, density and temperature. For example, some vector quantities in physics include displacement, velocity, acceleration, force and weight, momentum, electric field strength and gravitational field strength. Resultant vector. It is the total or net vector, which is the single vector that all vectors are combined. Vector quantities are represented by arrows. The arrowhead indicates the direction of the vector. The length of the arrow represents the magnitude. There are 2 methods that can be drawn to determine the resultant vector, as the triangle method and the parallelogram method. To add the vector A and vector B using the triangle method. Link the head of vector A to the tail of vector B. The resultant vector is formed by connecting the tail of the vector A to the head of the vector B. To add the vector A and vector B using the parallelogram method. Link the tails of the vector A and vector B. Draw a parallelogram with vector A and vector B as sides. The resultant vector is the diagonal of the parallelogram. Determine the resultant of 2 vectors at right angles. Find the resultant velocity of an airplane flying at 80 km per hour in a 60 km per hour crosswind. Find the resultant velocity using the calculation. Draw a parallelogram with 80 km per hour and 60 km per second as sides, which form to the rectangular. The resultant velocity is the diagonal of the parallelogram. We can calculate the magnitude of the resultant velocity using the Pythagorean theorem. Resultant velocity squared equals 80 squared plus 60 squared. Resultant velocity equals squared root of 80 squared plus 60 squared equals 100 km per hour. We can calculate the direction of the resultant velocity by the tangent ratio. The direction of the resultant velocity is the angle theta to the direction of wind's velocity. So, the direction of the resultant velocity is tan power minus 1 of 80 over 60 is equal to 53 degrees to 60 km per hour. Find the resultant velocity using the graphically. Set the scale 1 cm to 10 km per hour. Draw the velocity of 60 km per hour to right for 6 cm. Measure angle at the head of the 60 km per hour velocity using a protractor as 90 degrees. Link the head of the 60 km per hour velocity to the tail of the 80 km per hour velocity. Draw a velocity of 80 km per hour for 8 centimeters. The resultant velocity is formed by connecting the tail of the 60 km per hour velocity to the head of the 80 km per hour. Measure the length of the resultant velocity. So, magnitude of the resultant velocity is 10 centimeters times 10 km per hour equals 100 km per hour. Measure the angle between the 60 km per hour and resultant velocity. So, the direction of the resultant velocity is 53 degrees to 60 km per hour. Candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. Distance and displacement. You don't need to know about displacement for IGCSE, but it's useful to know it. When a ball travels along a circular track from point A to point B, the distance traveled from A to B is half of the circumference of the circle. The displacement is the diameter of a circle, and its direction point from A to B, or downward or south. When a ball travels back to point A, the distance traveled from point A to return at point A is equal to the circumference of a circle. The displacement is equal to 0. This is because the ball has returned to its original position. Therefore, we can deduce that distance is the total length of the path traveled by an object. Distance is a scalar quantity, which means that it has only magnitude and no direction, and its unit is meter. The displacement is the directed distance from the start to the end points. Displacement is a vector quantity, which means that it has both magnitude and direction, and its unit is meter. Speed and velocity. Speed is the distance moved per unit time. Speed is a scalar quantity, which has only magnitude. Its unit is meters per second. The average speed is the total distance moved to divide by total time. Velocity is a change in a displacement per unit time. Velocity is a vector quantity, which has both magnitude and direction. In one-dimensional motion, the sign, positive or negative, in front of the velocity indicates the direction of the object's motion. The unit of velocity is the same as the unit of speed, which is meters per second. The magnitude of velocity is equal to speed when an object travels in a straight line and does not change its direction. A car travels with constant speed up and down the hill as shown. While its speed remains constant, its velocity is not constant due to the changing direction of movement. A car traveling at an initial speed of u for t seconds reaches a final speed of v and covers a distance of s meters, and its acceleration is constant. In a diagram, the average speed is u plus v over 2. Total distance moved is s. Total time is t. Therefore, u plus v over 2 equals s over t. If u equals v, this means a car is traveling with constant speed. So, the average speed is v. Total distance moved is s. Total time is t. Therefore, v equals s over t. Acceleration. Acceleration is change in velocity per unit time. Acceleration is a vector quantity, which has both magnitude and direction. Its unit is meters per second squared. Therefore, the equation of acceleration is a equals v minus u over t. A is acceleration in meters per second squared. V is final velocity in meters per second. U is initial velocity in meters per second. And t is time taken in seconds. When u equals v, it indicates the car is traveling at a constant speed. The change in velocity is 0, the acceleration is also 0. When v is more than u, it indicates the car is speeding up. This positive change in velocity is called acceleration. When v is less than u, it indicates the car is slowing down. This negative change in velocity is called deceleration. If an object decelerates, we must put the negative sign into this equation and positive if it accelerates. If a car moves the same distance as 5 meters every second, this means that a car is traveling with constant speed of 5 meters per second, and acceleration is 0. If a car moves with increasing distance every second, this means that a car is traveling with increasing speed, and it is accelerating. If a car moves with decreasing distance every second, this means that a car is traveling with decreasing speed, and it is decelerating. Distance-time graph. The graph of distance against time as shown here. We draw a right triangle. Here is change in x, and the x-axis represents time. Here is change in y, and the y-axis represents distance. The gradient of graph is the ratio of the change in y-axis to change in x-axis. So, it is the ratio of the change in distance to change in time. Since the gradient of the graph is the speed of the object, a horizontal line graph with zero gradient indicates the speed is zero and no acceleration. So, the object is at rest. A straight line graph with constant gradient indicates the object is moving at a constant speed and no acceleration. A is steeper than B, so A has a higher speed than B. A curved graph with an increasing gradient indicates the object is moving at increasing speed, and it is accelerating. A curved graph with a decreasing gradient indicates the object is moving at decreasing speed, and it is decelerating. Finding the speed and average speed using distance-time graph. The distance-time graph is shown here. Between A to B shows that the gradient is increasing, so the speed is also increasing, and the object is accelerating. Between B to C shows that the gradient is constant, so the speed is also constant, and the acceleration is 0. We can find the constant speed by the gradient between B to C. We draw a right triangle. Here is change in x, or run, is equal to 20, minus 7.5 is equal to 12.5. Here is change in y, or rise, is equal to 45, minus 10 is equal to 35. Therefore, the speed is equal to 35 divided by 12.5 is equal to 2.8 meters per second. Between C to D shows that the gradient is decreasing, so the speed is also decreasing, and the object is decelerating. Between D to E shows that the gradient is 0, so the speed is 0, no acceleration, and the object is at rest. We can find the average speed between A to E by the total distance divided by total time taken. The total distance is 60 meters. The total time is 35 seconds. Therefore, the average speed is equal to 60 divided by 35 is equal to 1.71 meters per second. Speed-time graph. The graph of speed against time as shown here. We draw a right triangle. Here is change in x, and the x-axis represents time. Here is change in y, and the y-axis represents speed. The gradient of speed-time graph is the ratio of the change in y-axis to the change in x-axis. So, it is the ratio of change in speed to change in time. The velocity is speed in a given direction. Their magnitudes are equal when an object travels in a straight line and does not change its direction. Since the gradient of the graph is the acceleration of the object, the area under graph is the half of u plus v times t. This is the average speed. Since the area under graph is the distance moved. A horizontal line graph at the x-axis with zero gradient indicates the acceleration is 0 and a speed is 0, so the object is at rest. A horizontal line graph with zero gradient indicates the acceleration is 0 and the object is moving at constant speed of u. Since the distance moved is the area under graph, which is u times t. A straight line graph with a positive constant gradient indicates the acceleration is constant, and the object is moving at increasing speed. We can find the acceleration from v minus u over t. And the distance moved is the area under the graph, which is half of sum of u and v times t. A straight line graph with a negative constant gradient indicates the deceleration is constant, and the object is moving at decreasing speed. We can find the acceleration from v minus u over t. And the distance moved is the area under the graph, which is half of sum of u and v times t. A curved graph with an increasing gradient indicates the acceleration increases, and the object is moving at increasing speed. A curved graph with a decreasing gradient indicates the acceleration decreases, and the object is moving at increasing speed. Finding the acceleration and distance moved using speed-time graph. The speed-time graph is shown here. Between A to B shows that the gradient is increasing, so the acceleration is also increasing, and the speed increases. Between B to C shows that the gradient is positive constant, so the acceleration is also constant, and the speed increases. We can find the constant acceleration by the gradient of graph. We draw a right triangle. Here is change in x, or run, is equal to 20, minus 7.5 is equal to 12.5. Here is change in y, or rise, is equal to 50, minus 10 is equal to 40. Since the acceleration is equal to 40 divided by 12.5 is equal to 3.2 meters per second squared. Between C to D shows that the gradient is decreasing, so the acceleration decreases, and the speed increases. Between D to E shows that the gradient is 0, so no acceleration, and the speed is constant at 60 meters per second. Between E to F shows that the gradient is negative constant, so the deceleration is constant, and the speed decreases. We can find the constant deceleration by the gradient of graph. We draw a right triangle. Here is change in y, or rise, is equal to 0, minus 60 equals minus 60. Here is change in x, or run, is equal to 45, minus 32.5 is equal to 12.5. Since the deceleration is equal to minus 60 divided by 12.5 equals minus 4.8 meters per second squared. We can find the average speed by the total distance moved divided by total time taken. The total distance moved is equal to the area under graph. The area under between A to B is approximately to area at here. So we combine area under graph between A to B with area under between C to D as a rectangle. Since the area of this rectangle is equal to 60 times 7.5 is equal to 450 meters. Area under graph between B to C forms a trapezium shape. So it is equal to 0.5 times sum of 10 and 50 and times 12.5 is equal to 375 meters. Area under graph between D to E to F form a trapezium shape. So it is equal to 0.5 times sum of 5, and 17.5 times 60 is equal to 675 meters. The total area under graph is equal to 375 plus 450 plus 675 is equal to 1,500. The average speed is equal to 1500 divided by 45 is equal to 33.3 meters per second. Rounded to 3 significant figures. Free fall is the motion of an object under the influence of gravity only. If a feather and a bowling ball are dropped at the same time from the same position in air, the bowling ball will reach the ground first. This happens because air resistance has a greater effect on the feather due to its larger surface area. If a feather and a bowling ball are dropped at the same time from the same position in a vacuum, they will reach the ground at same time and same speed. This is because air resistance has no effect on them. This is called free fall, that applies to all objects regardless of their mass in a vacuum. Free fall describes the motion of an object under the influence of gravity only. We can conclude that there is no air resistance and only weight acting on the object. The object accelerates constantly towards the ground due to gravity. This acceleration is typically denoted by the symbol g and has a value of approximately 9.8 meters per second squared. When a ball is moving as free fall, its speed increases by 9.8 meters per second every second. This is because its acceleration is approximately constant at 9.8 meters per second squared. A ball is dropped at rest, its initial speed is 0 and its initial acceleration is 9.8 meters per second squared. After 1 second, the ball has descended and its speed increases from 0 to 9.8 meters per second. After 2 seconds, the ball has descended a greater distance than it did first second, and its speed increases to 19.6 meters per second. After 3 seconds, the ball has descended a greater distance than it did between 1 and 2 seconds, and its speed increases to 29.4 meters per second. After 4 seconds, the ball has descended a greater distance than it did between 2 and 3 seconds, and its speed at 4 seconds increases to 39.2 meters per second. The speed time graph of a free fall. The speed of a ball increases 9.8 meters per second every second. Therefore, we plot the graph with the following points. Time 1 second, speed is 9.8. Time 2 seconds, speed is 19.6. Time 3 seconds, speed is 29.4. Time 4 seconds, speed is 39.2. Then we draw a straight line from the origin. The speed time graph shows that the gradient is constant, which indicates that speed increases with constant acceleration of 9.8 meters per second squared. We can find the distance moved of the ball from the area under the graph. Distance moved between 0 and 1 second equals 0.5 times 1 times 9.8 is equal to 4.9 meters. Distance moved between 1 and 2 seconds equals 0.5 times sum of 9.8 and 19.6 and times 1 is equal to 14.7 meters. Distance moved between 2 and 3 seconds equals 0.5 times sum of 19.6 and 29.4 and times 1 is equal to 24.5 meters. Distance moved between 3 and 4 seconds equals 0.5 times sum of 29.4 and 39.2 and times 1 is equal to 34.3 meters. You see that the distance moved of a ball increases for 9.8 meters every second. The distance time graph of a free fall. We can plot the graph at 1 second, the distance 4.9 meters. At 2 seconds, the distance is 14.7 plus 4.9 is equal to 19.6 meters. At 3 seconds, the distance is 19.6 plus 24.5 is equal to 44.1 meters. At 4 seconds, the distance is 44.1 plus 34.5 is equal to 78.4 meters. Then we draw a best fit curve. From the distance time graph, shows that the gradient is increasing, which indicates that the speed is also increasing with constant acceleration of 9.8 meters per second squared. Candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. Mass and weight. Mass is a measure of the quantity of matter in an object. It resists change in its state of motion. This is called inertia. Mass is a scalar quantity, with only magnitude. Its unit is kilogram. Mass is constant anywhere in the universe. Weight is the gravitational force on an object that has mass due to the gravitational field strength it's in. Weight is a vector quantity, having both magnitude and direction. Its unit is Newton. Weight varies depending on the gravitational field strength, which can change throughout the universe. Gravitational field strength is the force per unit mass. The equation of gravitational field strength is G equals W divided by M, where G is the gravitational field strength in Newton per kilogram. It is equal to 9.8 Newton per kilogram at the Earth's surface. It is equivalent to the acceleration of free fall, which is 9.8 meters per second squared on the Earth's surface. Gravitational field strength is a vector quantity that points towards the center of mass. W is a gravitational force, or weight in Newton. M is a mass in kilogram. We can rewrite this equation to find weight as W equals M multiplied by G. Gravitational field is a region in which a mass experiences a force due to gravitational attraction. We can measure mass using an electric balance. Weight can be measured by a Newton meter or force meter. Weight is affected by the gravitational field strength on a mass, so it will vary depending on the location. However, mass is not affected by gravitational field strength, and will remain constant regardless of location. When an astronaut is on Earth, their mass is 75 kilograms. The gravitational field strength at the Earth's surface is 9.8 newtons per kilogram. Therefore, his weight is 75 times 9.8 is equal to 735 newtons. When an astronaut is on the Moon, their mass remains at 75 kilograms. However, their weight is less than on Earth by a factor of 6. This is because the gravitational field strength on the Moon is 1.6 newtons per kilogram, which is 6 times less than on Earth. Therefore, their weight is 75 times 1.6 is equal to 120 newtons. Any planet or star have different gravitational field strength, which depends on its mass. The gravitational field strength of the Sun and its planets are shown. Therefore, gravitational field strength varies depending on the mass and size of each planet. The greater the mass of a planet, the stronger its gravitational field strength. Candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. Density. Density is defined as mass per unit volume. We can express density with the symbol ρ and the following equation. ρ equals m divided by v, where ρ is density in kilogram per cubic meter or grams per cubic centimeters. M is mass in kilogram or gram. V is volume in cubic meters or cubic centimeters. Density is specific value for each material, meaning that same material will always have the same density. For example, let's say we know an unknown material with a mass of 2.41 kilogram and its volume of 125 cubic centimeters. To determine which material our unknown material is made of, we know the densities of gold, aluminum, and silver as shown in the table. Convert the mass from kilograms to grams first, as 2.41 times 1000 is equal to 2410 grams. So, the density of unknown material equals 2410 grams divided by 125 cubic centimeters equals 19.3 grams per cubic centimeters. Therefore, our unknown material is made of gold. The density of an object can explain whether it will float or sink in a liquid. If the density of an object is more than the density of liquid, the object will sink. If the density of an object is less than the density of the liquid, the object will float. For example, a block of aluminum will sink and settle to the bottom of a liquid. This shows that aluminum's density is more than liquid's density. A block of ice will float at the surface of liquid, but will be totally submerged. This shows that ice's density is equal to the liquid's density. A block of cork will float at the surface of a liquid, with some of it submerged. This shows that cork's density is less than liquid's density. Experiment to investigate the density of a regular object. 1. Measure the mass of a regular object using an electric balance, or a Newton meter. If a scale balance is used, the reading will be the mass of the regular object. If a Newton meter is used, the reading will be the weight of the regular object, then dividing it by 9.8 to get its mass. 2. Find the volume of a regular object by measuring its dimensions and calculating the volume using the formula. For example, a cube, measure the length of each side with a ruler. Calculate its volume using V equals side cubed. A cuboid, measure the length, width and height with a ruler. Calculate its volume using V equals length times width times height. A cylinder, measure the height with a ruler. Measure its diameter using a ruler and wooden blocks as shown. View the top and measure the distance between blocks at different positions to check for consistency. Calculate the radius of the cylinder by dividing the diameter by 2. Calculate the volume of cylinder using V equals pi r squared h. A sphere, measure the radius using the same method as for the cylinder. Calculate the volume of the sphere using V equals 4 over 3 pi r cubed. We should measure each length at different positions and find the average to get an accurate value. View the scale at a perpendicular angle to avoid parallax error. 3. We can calculate the density of each object using ρ equals m divided by v. Experiment to investigate the density of an irregular object that sinks in water, such as a stone. 1. We measure the mass of a stone using an electric balance, or a Newton meter as shown. 2. We measure the volume of a stone using a measuring cylinder, as follows. Fill the measuring cylinder with water. Read the initial volume, V1, by viewing the scale at perpendicular angle at the bottom of the meniscus as shown. Carefully place the stone into the water. The water level rise, as shown. Read the final volume, V2, by viewing the scale at a perpendicular angle at the bottom of the meniscus. The volume of the stone is the final volume, V2, minus the initial volume, V1. 3. We can calculate the density of a stone using ρ equals m divided by v. How to determine the volume of a piece of wood that floats in the water, such as a cork. Fill a measuring cylinder with water. Tie a thread to a stone, and place it into the water. Read the initial value, V1, by viewing the scale at a perpendicular angle at the bottom of the meniscus as shown. Remove the stone from the measuring cylinder by lifting it up by the thread. Tie the cork to the end of the thread. Lower the cork and stone into the measuring cylinder. Read the final volume, V2, by viewing the scale at a perpendicular angle at the bottom of the meniscus, as shown. The volume of the cork is the final volume, V2, minus the initial volume, V1. Candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. Forces. Force is a vector quantity that has both magnitude and direction. Its unit is the newtons. Effects of the forces on object. When forces act on an object, they can cause the object to change in shape, direction of moving, speed. Forces can be categorized into two main types: contact forces and non-contact forces. A contact force is a force that acts between two objects that are physically touching each other. When two objects collide or come into contact, they exert a force on each other. This force can cause a change in motion, direction, or shape of the objects. When your hand pushes the box, a contact force propels the box forward. This is called the pushing force. Normal reaction force is the perpendicular force that acts on an object when it is in contact with a surface. When you place a box on a table, the table exerts an upward force, normal force, to hold the book against gravity. Tension is the force in a string, spring, rubber band, or wire when it is stretched or compressed. When you pull a box with a rope to create tension in the rope, this tension is the pulling force transmitted through the length of the rope. Friction is the force that opposes the relative motion between two surfaces in contact. When you push a box, or pulling a box along the floor with a rope, friction acts in the opposite direction of your applied force. Air or liquid resistance, also known as drag force, is a resistive force that acts on an object moving through air or liquid. Upthrust force, or buoyancy force, is the upward force that acts on an object that is partially or fully submerged in a fluid. A non-contact force is a force that acts between two objects that are not physically touching. Non-contact forces act through a field, which is an invisible region of space that surrounds an object and exerts a force on other objects within that field. The gravitational force, or weight, due to the gravitational field strength of Earth. Its direction is always downward. Earth's gravity pulls objects towards its center, even without touching them. We can calculate the weight of the object using the equation W equals mg, where W is weight in newtons, m is mass in kilograms, and g is gravitational field strength in newtons per kilogram. Electrostatic force is the force between the charged objects. Charged objects attract or repel each other depending on their charges and distance between them. Like charges repel, unlike charges attract. Magnetic force is the force between the magnets. Magnets attract or repel each other without physical contact. Like poles repel, unlike poles attract. When a car is moving to the right as shown, there are the forces acting on a car including the weight acts downward. The total normal reaction force is acting upward at its wheels. The force from the engine acting forward. The air resistance acting backward. When a box is at rest on a rough incline as shown, there are the forces acting on a box including the weight acts downward. The normal reaction force acts upward perpendicular to the slope. The friction acts upward parallel to the slope. When we pull a box with a rope along the incline, causing the box to move up the incline, there are forces acting on the box including the tension acts up along the slope. The friction acts downward parallel to the slope, because the box is moving up the slope. The weight acts downward. The normal reaction force acts upward perpendicular to the slope. When a box floats on the water, there are forces acting on the box including the weight acts downward. The upthrust acts upward. When a metal sphere is moving downward through the water, there are forces acting on the metal including the weight acts downward. The upthrust acts upward. The water resistance acts upward. Resultant force. The resultant force, or net force, is the single force that has the same effect as all the other forces acting on an object combined. If the resultant force is zero, it is called balance force. If the resultant force is not zero, it is called unbalance force. We can find the resultant force that acting on the object, for example. A box A has forces acting on it as shown. The forces on the left and right sides of the box are balanced. This means the net force acting on the box in the horizontal direction is 0. In the vertical direction, the resultant force can be found by subtracting the downward force, 22 newtons, from the upward force, 14 newtons. So, a resultant force is 8 newtons acting downwards. A box B has the forces acting on it as shown. The resultant force can be determined by adding the two forces acting to the right, 300 newtons and 60 newtons. So, a resultant force is 360 newtons acting to the right. A box C has the forces acting on it as shown. The resultant force can be found by adding the two rightward forces, 2 newtons and 4 newtons, and subtracting the leftward force 5 newtons. So, a resultant force is 1 newton acting to the right. A box D has the forces acting on it as shown. The resultant force can be found by subtracting the leftward force of 70 newtons and the leftward force 30 and 20 newtons. So, a resultant force is 20 newtons acting to the left. Calculate the magnitude and direction of the resultant force of two forces acting at right angle as shown. First method. Calculate using trigonometry. Join the tail of 10 Newton and 8 Newton forces at right angle. Draw a parallelogram with 10 newtons and 8 newtons as sides, which form to the rectangular. The resultant force is the diagonal of the parallelogram. We can calculate the magnitude of the resultant force using the Pythagorean theorem. Resultant force equals 10 squared plus 8 squared equals 12.8 newtons. We can calculate the direction of the resultant force by the tangent ratio. The direction of the resultant force is the angle theta to 10 newtons force. So, the direction of the resultant velocity is tan power minus 1 of 8 over 10 is equal to 39 degrees to 10 newtons force. Second method. Find the resultant force using the graphical diagram. Set the scale 1 cm to 2 newtons. Parallelogram diagram. Draw the force of 10 newtons for 5 centimeters. Measure angle at the tail of the 10 newtons force using a protractor as 90 degrees. Link the tail of the 8 newtons force to the tail of the 10 newtons force. Draw a force of 8 newtons for 4 centimeters. Draw a parallelogram with 10 newtons and 8 newtons as sides, which form to the rectangular. The resultant force is the diagonal of the parallelogram. Measure the length of the resultant force. So, magnitude of the resultant force is 6.4 centimeters times 2 newtons equals 12.8 newtons. Measure the angle between the 10 newtons force resultant force. So, the direction of the resultant velocity is 39 degrees to 10 newtons force. Triangular diagram. Draw the force of 10 newtons for 5 centimeters. Measure angle at the head of the 10 newtons force using a protractor as 90 degrees. Link the tail of the 8 newtons force to the head of the 10 newtons force. Draw a force of 8 newtons for 4 centimeters. The resultant force is formed by connecting the tail of the 10 newtons force to the head of the 8 newtons force. Measure the length of the resultant force. So, magnitude of the resultant force is 6.4 centimeters times 2 newtons equals 12.8 newtons. Measure the angle between the 10 newtons force resultant force. So, the direction of the resultant force is 39 degrees to 10 newtons force. The three laws of motion, also known as Newton's laws of motion. Newton's first law of motion. The forces on an object are all balanced, then it will just stay still, or else it is already moving, it will just carry on at the constant velocity. When a car is at rest, then the forces on it must be balanced. So, Car's weight acts downward to equal the total normal forces acting upward. When you pushes a car with a force 500 newtons to the right, and a car stays still, this causes the total friction between the tires and the road's surface to act to the left, 500 newtons, for balancing with the pushing force. When a car is moving with constant velocity, then the forces on it must be balanced. So, car's weight acts downward to equal the total normal forces acting upward. The force from engine, 2,500 newtons, acting forward is balanced with the fair resistance, 2,500 newtons, acting backward. When a ball is falling down with constant velocity, then the forces on it must be balanced. The downward weight, 10 newtons, is balanced with the total upward upthrust, 1 newton, and air resistance, 9 newtons. Since, we can conclude that, when no resultant force or balanced force, the object is stationary, or moving with constant velocity, and its acceleration is zero. Newton's second law of motion. If there is a resultant force, unbalanced force, then the object will accelerate in that direction. This acceleration can be done by changing the object's velocity. The change in velocity causes the object to start, speeding up, slowing down, stop, and changing direction. If a resultant force acts on an object at rest, the object will accelerate, starting to move, increasing its speed. If a resultant force acts on an object in the opposite direction of its motion, the object will decelerate, eventually coming to a stop. If a resultant force acts on an object in the same direction of its motion, the object will accelerate, further increasing its speed. If a resultant force acts on an object at a perpendicular angle to its direction of motion, the object will change direction, while its speed remains the same. The acceleration of an object is directly proportional to the resultant force. The bigger the force, the greater the acceleration. The acceleration is inversely proportional to mass of the object. The bigger the mass, the smaller the acceleration. This can be expressed mathematically as F equals ma, where F is the resultant force in newtons, m is the mass in kilograms, a is the acceleration in meters per second squared. For example, find the resultant force and acceleration of the box, with magnitude and direction like as shown. The resultant force is the subtracting the leftward force 15 newtons with the rightward forces 4 newtons and 2 newtons, resulting 9 newtons to the left. Calculate the acceleration using F equals ma. Substitute F equals 9 newtons, mass equals 2 kilograms. Then A equals 9 divided by 2 is equal to 4.5 meters per second squared to the left. Newton's third law of motion. When object A exerts a force on object B, then object B exerts an equal and opposite force on object A. A pair of forces must be equal in magnitude, opposite in direction, and act on different objects. For example, a book lying on a table exerts a downward force on the table. This is the action force. The table also exerts an equal and opposite force on the book in the upward direction. This is the reaction force. The earth exerts a downward force on the book. This is the action force. The book also exerts an equal and opposite force on the earth in the upward direction. This is the reaction force. While moving on the ground, we push the ground backward with our feet. This is the action force. The ground also exerts a forward force on our feet of equal magnitude in the opposite direction, which makes us move forward. This is the reaction force. A man's hand exerts a force on the wall. This is the action force. The wall also exerts an equal and opposite force on a man's hand in the backward force. This is the reaction force. A rocket exerts a downward force on the burnt gases. This is the action force. The burnt gases also exerts an equal and opposite force on the rocket in an upward direction. This is the reaction force. Friction. Friction is a force that opposes the movement of an object. It acts in the direction opposite to the motion. Friction is present almost everywhere, and it can slow down, or even stop moving objects. This happens because friction converts kinetic energy into thermal energy. If there's no force propelling an object forward, friction will eventually slow it down to a complete stop. This is true on Earth, but in a frictionless environment like outer space, objects can continue moving indefinitely. To maintain a constant speed, an object needs a continuous driving force to overcome friction. There are three main types of friction. Static friction. This occurs between two solid surfaces that are at rest and not moving relative to each other. It prevents an object from slipping. Static friction is usually the greatest force you need to overcome to get an object moving. Kinetic friction, sliding friction. This occurs between two solid surfaces that are sliding past each other. It is the force you feel when you rub your hands together or slide a box across the floor. Kinetic friction is usually slightly less than static friction. You can reduce both static and kinetic friction by using lubricants like oil or grease between the surfaces. Fluid friction, also known as drag. This is the resistance an object experiences when moving through a fluid, liquid, or gas. There are two main factors affecting fluid friction. The surface area of the object in contact with the fluid increases, drag also increases. Streamlined shapes, like those of race cars or boat hulls, experience less drag. This is because they deflect the fluid more smoothly, resulting in less resistance to the object's movement. The object's speed increases, drag also increases. Terminal velocity is the maximum speed an object reaches when moving through a fluid, liquid, or gas, due to the balance forces, no resultant force. When an object is moving through a fluid, there is a drag force due to the fluid. This drag force can increase when the speed of the object increases and the surface area of the object increases. Right now, we will use the symbol of sigma F to represent the resultant force. Consider the terminal velocity of a skydiver. When a skydiver jumps out of airplane, they are initially at rest. Drag force is zero because their speed is zero. Only weight acts on them downward, so the resultant force is equal to their weight. Since their initial acceleration is 9.8 meters per second squared. This causes their speed to increases from zero, and the drag force also increases. As time passes, drag force acts upward to increase as speed increases. The resultant force is equal to their weight, minus drag force, which acts downward to decrease. This causes their acceleration also decreases. As drag force increases until it equals their weight. This causes the resultant force is zero. Since their acceleration also is zero. This causes their speed is constant. This is called terminal velocity. When a parachute is opened, the large surface area increases the drag force to act upward. This causes the resultant force to be drag force, minus their weight, which acts upward. Since the acceleration is also upwards, so the skydiver decelerates, and their speed decreases. As time passes, the drag force acts upward to decrease as speed decreases. Since the resultant force acts upward to decrease, and their deceleration also decreases. As the drag force decreases until it equals their weight, so the resultant force is zero. This causes their acceleration is also zero, and their speed is constant again. This speed is called terminal velocity. The speed-time graph of the skydiver's motion is shown on the screen. We know that the gradient of speed-time graph is the acceleration. At point A, initial speed is 0 and initial gradient is 9.8. This is because the initial acceleration is 9.8 meters per second squared. Between points A and B, the gradient decreases. This means that the acceleration also decreases, while the speed still increases. Between B and C, the speed is constant and this speed is called terminal velocity. The gradient of graph is zero. This means that the acceleration is also zero. At point C, the parachute is opened, large surface area of the parachute, causing large drag force. This causes the speed to decreases rapidly. Between C and D, the speed decreases. The gradient is negative, so the parachutist decelerates. The steepness of the gradient decreases, so the deceleration also decreases. Between D and E, the speed is constant, which is terminal velocity. The gradient is zero. This means that the acceleration is also zero. The parachutist reaches the ground at point E. The speed-time graph showing the difference between free fall and terminal velocity of a ball. When a ball falls through a vacuum, there is no air resistance acting on it. This is called free fall. The speed-time graph of this scenario is a straight line passing through the origin. The constant gradient represents the ball's constant acceleration due to gravity, which is around 9.8 meters per second squared. This is because only force acting on the ball is its weight acting downwards, so the resultant force is the weight. When a ball falls through air, there is air resistance acting on it. The speed-time graph of this scenario is a curve with a decreasing gradient that eventually becomes horizontal. The initial gradient is around 9.8 meters per second squared, represents the ball's acceleration due to gravity. This is because at the beginning, the only force acting on the ball is its weight acting downwards, making the weight the initial resultant force. Over time, the decreasing gradient of the graph shows that the acceleration of the ball decreases. This is because as the ball falls faster, air resistance also increases. This air resistance acts in the upward direction, opposing the weight. So, the resultant force is the weight minus the air resistance, becomes smaller as air resistance increases. When the gradient reaches zero, it indicates that the acceleration is also zero. This causes the speed of the ball is constant, and reaches its terminal velocity. At terminal velocity, the air resistance acting upwards is equal to the weight acting downwards. Since the resultant force is zero, a ball falling through air will take longer and reach the ground at a slower speed compared to a ball falling through a vacuum from the same height. Deformation of material. Investigate how extension varies with applied force for helical springs. Set up the apparatus as shown. Measure the original length of the unstretched spring using a ruler. Hang a load 1 north on the spring, and then measure the length of the spring. Calculate the extension by subtracting the length from the original length. Repeat the experiment for addition loads of 2 newtons, 3 newtons, 4 newtons, 5 newtons and 6 newtons. Record the results of the length of the spring and its extension in the table. Plot the graph of the load in newtons against the extension in centimeters as shown. We can conclude the results from the graph as follows. Here the result is a straight line graph passing through the origin of the axis. This shows that the spring obeys Hooke's law. Hooke's law states the extension of the spring, string or wire is directly proportional to the force, or load. In this region, the spring is not obeys Hooke's law. At this point is called the limit of proportionality. It is the point where the spring stops obeying Hooke's law and starts to stretch more for each increase in the load force. At this point is called the elastic limit. If the spring is stretched beyond its elastic limit, it will not return to its original length when the weights are removed. Investigate how extension varies with applied force for elastic bands. We set up the apparatus, as shown, to investigate how an elastic band stretches under load. If you stretch an elastic band with increasing load forces, we get a graph of load against extension like as shown. The graph is not a straight line, showing that elastic bands do not obey Hooke's law. If the graph of load against extension of material when it loaded and unloaded like as shown. This shows that this material stretches elastically. This is called elastic deformation. This means that a wire, spring or rubber band that stretches elastically will return to its original length once the stretching force is removed. If the graph of load against extension of material when it loaded and unloaded like as shown. This shows that this material stretches plastically. This is called plastic deformation. This means that a wire, spring or rubber band that stretches plastically will not return to its original length once the stretching force is removed. Circular motion. When a resultant force, or sigma F, acts on a ball in perpendicular angle to the direction of motion, this causes the direction of motion to change, but the speed remains constant. If this resultant force acts on a ball continuously, this causes the ball to move in a circular path, as shown on the screen. We can conclude the following about circle motion. There is the resultant force known as the centripetal force. It acts on an object at a right angle to the direction of motion. This force always acts towards the center of the circle. This resultant force changes the direction of the object's motion at any point in the circular path, while the object's speed remains constant. This continuous change in direction is what keeps the object in the circular path. This resultant force causes an acceleration that is directed towards the center of the circle. This acceleration is called the centripetal acceleration. If this resultant force absent, the object will escape from the circular path along a tangent line at the point where it leaves the circle. The resultant force, or centripetal force, is increased as the speed of an object increases. The mass of an object increases. The radius of the circular path decreases. Vertical circular motion of a ball that attaches to a string. The resultant force, also known as the centripetal force, is provided by the tension in the string and the component of weight. If the speed of the ball increases, the resultant force needs to increase as well to keep the ball moving in a circular path. This increase in speed also causes the tension in the string to increase. If the tension increases until it can no longer support the resultant force, the string breaks. The ball then escapes from the circular path along a tangent line at the point of breakage. If the string breaks at point A, this causes the object escapes from the circular path along the tangent line at the point A, and then it is pulled downward from the weight to the ground. This cause the traveling path is curve as shown. If the string breaks at point B, this cause the object escapes from the circular path along the tangent line at the point A, and then it is pulled downward from the weight to the ground. This cause the traveling path is curve as shown. If the string breaks at point C, this cause the object escape from the circular path as shown. Horizontal circular motion. Horizontal circular motion of a ball that is attached to a string. The resultant force, or centripetal force, is provided by the tension in the string. If the speed increases, the resultant force and tension increase, with mass and radius remain constant. If the radius decreases, the resultant force and tension increase, with mass and speed remain constant. If the mass increases, the resultant force and tension increase, with speed and radius remain constant. A car is moving on a circular road. The resultant force, or centripetal force, is provided by the sideways friction between the surface of the car's tires and the road. If the speed of a car increases, the resultant force increases, which causes the sideways friction between the surface of the car's tires and the road to increases. If the sideways friction is not enough to support the resultant force, this causes the car to escape from the circular road. The moon orbits the Earth in a circular path. The resultant force is provided by the gravitational force between the moon and the Earth. Candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. Turning effect of forces is a measure of the moment forces. When forces act around a fixed point called a pivot, they have turning effects called moments. We use these effects all the time in everyday life. For some everyday examples, as a spanner or wrench uses to loosen a nut, you apply a force that creates an anticlockwise moment, helping you turn the nut. A claw hammer uses to remove a nail. The force applied on the handle to create the moment of force. A scissors work by applying two opposing forces that create a moment, causing the blades to come together and cut through a material. A seesaw pivots on a central point, and the moment created by children sitting on either end determines its clockwise or anticlockwise movement. A lever is tools that utilize the concept of moment of force to amplify the applied force, making it easier to lift or move heavy objects. A door is opened by pushing or pulling on a doorknob. You create a moment of force that causes the door to rotate on its hinges. A wheelbarrow distributes the weight of a heavy object, allowing you to apply a smaller force at the handles to move it with a larger moment. Steering wheels of a car is turned to create a moment that alters the direction of the wheels, ultimately controlling the car's direction. Moment of forces is defined as the product of force and perpendicular distance between line of action and pivot. We can write the equation as m equals Fd, where m is the moment of force in Newton meter, F is force in newtons, d is perpendicular distance from pivot in meters. For first example, a 4 newtons force acts on the light beam at a perpendicular distance of 3 meters from the pivot. This causes the clockwise moment to be 3 times 4 is equal to 12 newton meters about the pivot. Second example, a 3 newtons force acts on the light beam at a perpendicular distance of 2 meters from the pivot. This causes the anticlockwise moment to be 3 times 2 is equal to 6 newton meters about the pivot. Third example, a 4 newtons force acts at the end of beam along pivot, as shown. This causes the moment is 0 due to the force acting along the pivot, causing perpendicular distance from pivot to be 0. Fourth example, a 5 newtons force acts at the end of beam, and 2 meters perpendicular distance between line of action and pivot. This causes the anticlockwise moment to be 5 times 2 is equal to 10 newton meters about the pivot. Fifth example, a diagram shows the forces acting on a light beam and distance of each force from point P. Calculate the sum, or resultant, moment about P. Clockwise moment about P causes by forces 3 newtons, 1 meter from P and 4 newtons, 3 meters from P. So, total clockwise moment equals 4 times 3 plus 3 times 1 is equal to 15 newtons meter. Anticlockwise moment about P causes by only 2 newtons, 1 meter from P. So, anticlockwise moment equals 2 times 1 is equal to 2 newtons meters. You see that larger total clockwise moment than anticlockwise moment, so the resultant moment equals 15 minus 2 is equal to 13 newtons meter in clockwise. The principle of moment states that if an object is in equilibrium, the total of clockwise moment is equal to the total anticlockwise moment about the pivot. The conditions for equilibrium of an object are: there is no resultant force acting on the object. There is no resultant moment acting on the object. This is the principle of moment. For example, someone is trying to balance a plank with particles A and B. The plank has negligible weight. Calculate the moment of the forces about point O and determine if the plank will balance. If not, calculate the force acting on the plank at P. Calculate the moment of 4 newtons force about point O, which is 4 times 4 is equal to 16 newton meters in clockwise. Calculate the moment of 6 newtons force about point O, which is 2 times 6 is equal to 12 newton meters in anticlockwise. Since the clockwise moment is greater than the anticlockwise moment, the plank will rotate clockwise. Resultant moment equals 16 minus 12 is equal to 4 newtons meter. To balance the plank, we need to add an additional downward force at point P that will create anticlockwise moment of 4 newton meters. Perpendicular distance between point P to pivot O is 4 meters. So, force F equals 4 divided by 4 is equal to 1 newton. Therefore, the plank will balance if a force of 1 newton is applied downward at point P. Candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. Center of gravity. The center of gravity is sometimes called the center of mass. It is the point where the whole of the weight of the object appears to act. The weight of all object acts through the center of gravity. For example, the center of gravity of the human is about here. The center of gravity of an apple is about here. The center of gravity of a magnet is here. A uniform object's center of gravity is at the middle of the object. For example, a uniform cylinder has its center of gravity at here. A uniform sphere has its center of gravity at the center. A uniform cube has its center of gravity at here. A uniform wooden meter rule has its center of gravity at the 50 centimeters mark. The object will always balance around its center of gravity. For example, the wooden meter rule is balancing on the pivot at the 50 centimeters mark, like as shown. You can try balancing a pencil on your finger, like as shown. The people is walking on the rope, like as shows. An object will be nice and stable if it has low center of gravity and wide base area. For example, a conical frustum placed with its wider base on the ground is more stable than when flipped upside down. In the first case, the center of gravity is lower and the base area is wider, so more stability. The second case, the center of gravity is higher and the base area is smaller, so less stability. A racing car has a lower and wider base area than the family car, so the racing car is more stable. An object will topple over if a vertical line drawn downward from its center of gravity falls outside its base area as shown. For example, a bus on an incline road will stay on the incline as long as the vertical line from the center of gravity falls on its base. However, if the slope increases until the vertical line falls outside its base area, the bus will topple over. Experiment to investigate the center of gravity of an irregular lamina. Hang up the lamina as shown. Suspend a plumb line from the same plane. Mark the position of the thread as shown. The center of gravity is along the line of the thread. Repeat the experiment with the lamina suspended from the different places. The center of gravity is where these lines cross. Someone of weight 500 newtons is standing on a uniform plank 6 meter long and weighing 250 newtons. The plank is supported by 2 trestles as shown. Calculate the upward forces X and Y exerted by the trestles on the plank. The plank is uniform, so the center of gravity is the middle of the plank equals 2.5 meters from trestle Y. The plank is equilibrium because it is at rest and not turning. So, the principle of moments can be applied. Finding X, let's take trestle Y as the pivot. The total clockwise moment about Y equals the total anticlockwise moment about Y. Total clockwise moment, 5 times X, and equal to total anticlockwise moment, 500 times 3 plus 250 times 2.5. We will get 5x equals 2125. So, x equals 425 newtons. Finding y using total upward force on the plank equals total downward force on the plank, because no resultant force acts on the plank. Total upward force is 425 plus y equals total downward force is 500 plus 250. So, y equals 325 newtons. A diagram shows an arm with the hand holding a weight of 120 newtons. The 20 newtons force is the weight of the forearm, acting at the center of gravity. F is the force in the muscle of the upper arm. P is the point in the elbow about which the arm pivots. The distances of the forces from point P are shown. By taking moments about point P, calculate the force F. A diagram shows an arm is equilibrium, or balance, so total clockwise moment equals total anticlockwise moment. Total clockwise moment causes by 20 newtons force, 15 centimeters from P, and 120 newtons force, 33 centimeters from P. So, total clockwise moment is 20 times 15 plus 120 times 33, is equal to 4,260 newtons meter. Total anticlockwise moment is force F times 2. Therefore, force F is 4,260 divided by 2 is equal to 2,130 newtons. A force acts on the forearm at point P. Calculate this force and state its direction. We can apply the total upward acting on arm equals total downward force acting on arm, due to equilibrium of arm. Total upward force equals 2,130 newtons. Total downward force equals 20 plus 140 is equal to 140 newtons. Total upward force is more than total downward force. To balance the arm, we need to add an additional downward force at point P. The magnitude of this force equals 2,130 minus 140 is equal to 1,990 newtons. Candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. Momentum is a measure of the tendency of an object to keep moving, or of how hard it is to stop it moving. Momentum is defined as the product of mass and velocity. We can write the equation of the momentum as P equals mv, where P is momentum in Newton second or kilogram meter per second. M is mass in kilogram. V is the velocity in meter per second. Momentum is a vector quantity due to the velocity is vector, so the direction of momentum is same as the direction of velocity. For example, a 1,200 kilogram car is stationary, so its momentum is 0. This is because its velocity is 0. When this car is moving with 25 meters per second, its momentum is 1,200 times 25 is equal to 30,000 kilograms meter per second. The same car is moving and it has momentum of 45,000 kilograms meter per second. To find the car's velocity, we can substitute P equals 45,000 kilograms meter per second, m equals 1,200 kilograms. So, its velocity is 45,000 divided by 1,200 is equal to 37.5 meters per second. Momentum, Newton's second law of motion, acceleration and impulse. From Newton's second law of motion, F equals ma. From the acceleration of the object, the equals v minus u over t. We combine two equations together as we get F equals mv minus mu over t. This is the change in momentum per unit time. We can conclude that the resultant force is the rate of change in momentum. We can write the equation as shown. where F is the resultant force in Newton. mv is final momentum. mu is initial momentum. T is time in second. The change in momentum is defined as the impulse. So, the impulse is equal to mv minus mu, or equal to ft. The impulse is defined as the change in momentum. It's also the product of force and time. The impulse is a vector quantity, just like momentum, because both depend on the direction of motion. Its unit is kilograms meter per second, which is also equal to Newton second. This is the same unit as momentum. Work example 1. A 2000 kilograms car accelerates from 10 meters per second to 25 meters per second in 10 seconds. What resultant force produced this acceleration? We substitute m is 2000 kilograms, v is 25 meters per second, u is 10 meters per second, and t is 10 seconds. So, the resultant force is 3000 newtons. Work example 2. The first stage of the type of rocket used in moon missions provides an unbalanced upward, away from the Earth, force of 30 meganewtons, and burns for 2.5 minutes. Calculate the increase in the rocket's momentum that results. Convert 30 meganewtons into newtons. It is 30 times 10 to the power of 6 newtons. Convert 2.5 minutes into seconds. It is 2.5 times 60 is equal to 150 seconds. Change in momentum is mv minus mu equals ft. So, increase in momentum equals 30 times 10 to the power of 6 times 150 is equal to 4.5 times 10 to the power of 9 kilograms meters per second. If the rocket has a mass of 3000 tons, what is the velocity of the rocket after the first stage has completed its burn? Convert 3000 tons into kilograms. It is 3000 times 1000 is equal to 3 times 10 to the power of 6 kilograms. The rocket starts from rest, so u equals 0 and then mu equals 0. Increase in momentum equals mv. Substitute the increase in momentum equals 4.5 times 10 to the power of 9, and m equals 3 times 10 to the power 6. So, v equals 1500 meters per second. Momentum in collision. The total momentum of objects that collide remains the same. This is called the conservation of momentum. Since total momentum of the system before collision is equal to the total momentum of the system after collision. Let's consider a moving ball A with mass m1 rolls towards stationary ball B with mass m2. So, total momentum before collision is m1u. The balls after the collision have the velocities as shown. So, total momentum after collision is m1 v1 plus m2 v2. During the impact, each ball exerts a force on the other with equal in size and opposite in direction. This is because Newton's third law about action and reaction. These forces act each ball for the same amount of time. This equates to F times t being equal in magnitude, but opposite in direction for each ball. Fa times t is the impulse on A. Fb times t is the impulse on B. The negative shows that both impulses are in opposite direction. So, the impulse on A is equal in magnitude, but opposite in direction to the impulse on B. Consequently, the change in momentum of ball A is equal in size, but opposite in direction to the change in momentum of ball B. This ensures that the total momentum before the collision remains equal to the total momentum after the collision. Work example 3. Find the speed of ball B after the collision like as shown. We given the sign of velocity's direction to the right is positive, and to the left is negative. The total momentum before collision is the sum of ball A's momentum and ball B's momentum, which is 0.4 times 2.5 plus 0.6 times minus 1.2, it is equal to 0.28 kilograms meters per second. The total momentum, after collision, is 0.4 times, minus 0.5 plus 0.6 times v. It is equal to minus 0.2 plus 0.6 ev kilograms meters per second. The total momentum before collision is equal to the total momentum after collision, and then v is 0.8 meters per second, to the right due to the positive sign. Therefore, speed of ball B after collision is 0.8 meters per second. Work example 4. Find the impulse on a ball A and the speed of the ball B after the collision. We given the sign of velocity's direction to the right is positive, and to the left is negative. Impulse on A equals mv minus mu. Substitute m equals 0.5, v equals 2.5 and u equals 4. Its result is minus 0.75 kilograms meter per second to the left. The impulse on B is equal to the impulse on A equals 0.75 kilograms meter per second to the right. The direction of impulse on B is opposite to the impulse on A. The impulse on B is equal to mv minus mu. Substitute the impulse on B equals 0.75, m equals 0.3 and u equals 2. So, v equals 4.5 meters per second to the right. Momentum in explosion. The conservation of momentum principle can be applied to explosions. The total momentum of the system before the explosion is equal to the total momentum of the system after the explosion, although there will be a significant increase in the total kinetic energy of the fragments. An explosion involves a rapid release of energy, causing an object to break apart into pieces that fly in different directions. Let's consider an object with mass m that is stationary before the explosion, so its momentum is 0. The object explodes into two fragments with masses m1 and m2, which move apart at velocities v1 and v2, respectively. The total momentum after the explosion is the sum of the momenta of the two fragments, m1 v1 plus m2 v2. Momentum is conserved when during explosion. So, total momentum before explosion equals total momentum after explosion. Then, 0 equals m1 v1 plus m2 v2. And m1 v1 equals minus m2 v2. This equation tells us that the momentum of fragment m1 is equal in magnitude, but opposite in direction to the momentum of fragment m2. As the rocket burns the fuel, generating hot gases that are ejected at high speeds from the rocket. This produces the momentum large amount of fast-moving gases out of the back of the rocket. So, the rocket gains an equal amount of momentum in the opposite direction to that of the moving exhaust gases. Momentum in safety car. A larger force means a faster change of momentum, and so greater acceleration. Likewise, if someone's momentum changes very quickly, like in a car crash, the forces on the body will be very large, and more likely to cause injury. Cars are now designed with various safety features that increase the time over which the car's momentum changes in an accident. Crumple zones, airbags, and seat belts in a car increase the collision time. Crumple zones on impact, increasing the impact time taken for the car to stop. Airbags slow you down more gradually, increasing the impact time. This reduces the force acting on the body. Seat belts stretch slightly, increasing the time taken for the wearer to stop. This reduces the forces acting on the chest. For example, a car traveling at 20 meters per second collides with a wall and is brought to rest in just 0.02 seconds. A man in the car has a mass of 50 kilograms. He experiences the same deceleration when he comes into contact with a hard surface in the car, such as the dashboard or the windscreen. What force does the person experience? To find the force acting on the person by this equation, We substitute m is 50 kilograms, v is 0 meters per second, u is 20 meters per second, and t is 0.02 seconds. So, the resultant force is 50,000 newtons. Candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. Energy is the ability of a body to do work. Its unit is either newtons meter or joule. Energy is scalar quantity, meaning that it has only magnitude. Here are different forms of energy. Kinetic energy is the energy possessed by a mass due to its movement. Its formula can be written as E(k) equals half of m(v) squared, where E(k) is the kinetic energy in joules. M is the mass in kilograms. V is the speed in meters per second. Gravitational potential energy is the energy stored in a mass due to its position in a gravitational field. Its formula can be written as EP equals mg delta H, where EP is the gravitational potential energy in joules. M is the mass in kilograms. G is the acceleration due to gravity equals 9.8 meters per second squared. Delta H is the change in height in meters. Mechanical energy is the sum of the kinetic energy and potential energy of a system. Elastic potential energy is the energy stored in an object due to changes in its shape. Chemical potential energy is the energy stored within the chemical bonds between atoms or molecules. Electrical potential energy is the energy stored in the charges under an electrical field. Nuclear energy is the energy stored in the nucleus. Thermal, or heat, energy, also known as internal energy, is the energy refers to the energy contained within a system that is responsible for its temperature. Radiation energy is an electromagnetic radiation, such as light, infrared radiation. Sound is the energy transferred through the vibration of the particles in matter. Work done is the product of force and distance moved in the direction of the force. Its unit is either newtons meter or joules. Work is the scalar quantity, which has only magnitude. The equation for work done can be written as W equals F multiplied by D, where W represents the work done in joules. F is force in newtons, and D is the distance moved in the direction of force in meters. For example, a force of 5 newtons acts on a box, causing it moves in the direction of force for a distance of 10 meters. Therefore, work done is 5 times 10 is equal to 50 joules. On the other, if a force of 5 newtons acts in the opposite direction of the distance moved, which is negative direction, therefore, work done is minus 5 times 10 equals minus 50 joules. When the person is walking of 10 meters and holding the box with weight of 10 newtons. A person walks 10 meters while holding a box weighing 10 newtons, the person exerts a force of 10 newtons to hold the box, but the box moves forward in a direction perpendicular to the force. Therefore, the work done by the person holding the box is 0. In another scenario, if a person with a weight of 600 newtons walks up a stairs with a height of 5 meters and a horizontal length of 6 meters. Therefore, the work done by the person is 600 times 5 is equal to 3000 joules. This is because the weight of the person and the height of the site of the stairs are parallel. In a case of a package with weight of W moving along a conveyor belt driven by a motor as shown. Therefore, the work done on the package is W times h. This is because the weight of the package is parallel to the height h. A 300 newtons force is applied to a box to move it up a ramp, as shown. Therefore, the work is done by the force when moving the box from x to y is 300 times 5, is equal to 1,500 joules. This is because the force of 300 newtons is parallel to 5 meters. Work done and the energy principle state that the work done is equal to the energy transferred. We can express this relationship with the equation W equals F D equals delta E, where W represents the work done in joules, F represents the force in newtons, D represents the distance moved in meters, delta E represents the energy transferred. For example, let's consider a mass of 5 kilograms with an initial speed 2 meters per second. It is continuously exerted to a force of 10 newtons for 5 meters on a smooth surface. We need to find the final speed, v, at 5 meters. The work done by the force of 10 newtons is transferred to the kinetic energy, without any thermal losses due to friction since the surface is smooth. Therefore, the work done is equal to the increase in kinetic energy. The work done by the force of 10 newtons is 10 times 5. The increase in kinetic energy is half of 5 times v squared, minus half of 5 times 2 squared. Solving these equations, we find that the final speed, v, is 4.9 meters per second. In another scenario, let's the same box with an initial speed of 2 meters per second. It is exerted to a force of 10 newtons along a rough surface for a distance of d meters. As a result, 5 joules of thermal energy is lost, and the final speed is 5 meters per second. We need to find the distance moved by the box. The work done by the force of 10 newtons is transferred to both kinetic energy and thermal energy. So, we have the equation 10 times d equals half of 5 times 5 squared, minus half of 5 times 2 squared plus 5. Solving this equation, we find that the distance moved, d, by the box is 5.75 meters. In another scenario, let's consider a box with a mass of 5 kilograms being lifted from the ground to a higher level with a height of 3 meters. The weight of the box is 5 times 10 is equal to 50 newtons. The work done by the weight of the box is given by its weight multiplied by the height. Its result is 50 times 3 is equal to 150 joules. The gravitational potential energy increases by mgh equals 5 times 10 times 3. Its results is 150 joules. Therefore, the work done by the weight of the box is equal to the increasing in gravitational potential energy. The principle of the conservation of energy states that the energy cannot be created and destroyed, but can only be transferred from one form to another. For example, let's consider a mass of 1.5 kilograms that is dropped from rest to the ground from a height of 5 meters, neglecting air resistance. At the initial position, the mass has zero kinetic energy due to its zero speed, while gravitational potential energy is maximized at the greatest height. The maximum gravitational potential energy is mgh equals 1.5 times 9.8 times 5 is equal to 73.5 joules. The total mechanical energy of the system is the sum of its kinetic energy and gravitational potential energy, which in this case is 73.5 joules. It remains constant at any positions. As the mass moves downward, its height decreases, leading to a decrease in gravitational potential energy. This gravitational potential energy transfers into kinetic energy, causing the speed to increase. When the mass reaches the ground with a speed, v, its gravitational potential energy becomes zero since the height is zero. At this point, all gravitational potential energy have been transferred to kinetic energy. To find the speed, v, to at which it reaches the ground, we can apply the principle of conservation of energy. The decrease in gravitational potential energy is equal to the increase in kinetic energy. Using the equation mgh equals half of m times v squared, we can rearrange it to v equals square root of 2gh. Substituting the values in g equals 9.8 and h equals 5. Solving this equation, the speed, v, equals 9.9 meters per second. If air resistance is present, the speed, v, at which it reaches the ground will be less than 9.9 meters per second, because some energy is lost to thermal energy due to air resistance. In another scenario, let's assume mass being thrown upward through the air with an initial speed 10 meters per second. At the initial position, the mass has zero gravitational potential energy due to its zero height from the ground, while kinetic energy is maximized at the greatest speed. The maximum kinetic energy is half of 1.5 times 10 squared equals 75 joules. As the mass moves upward, its speed decreases, leading to a decrease in kinetic energy. This kinetic energy is transferred to gravitational potential energy and thermal energy due to air resistance. When the mass reaches the maximum height, its speed is zero, so its kinetic energy is zero. At this point, all of the kinetic energy is transferred to gravitational potential energy and thermal energy due to air resistance. To find the maximum height that the mass reaches, we can apply the principle of conservation of energy, assuming a thermal energy loss of 15 joules due to air resistance. The decrease in kinetic energy is equal to the increase in both gravitational potential energy and thermal energy. Using the equation half of m times v squared equals m, g, h, plus thermal energy lost, we can substitute the values in m equals 1.5, v equals 10, g equals 9.8 and thermal energy lost equals 15. Solving this equation, we find that the height, h, equals 4.1 meters. If air resistance is ignored, the height at which it reaches from the ground will be greater than 4.1 meters, because there will be no thermal energy lost due to air resistance. In another scenario, let's consider a pendulum with a mass of 0.6 kilograms being oscillated at rest from A to point B, and then to point C, neglecting air resistance. The total mechanical energy of the system remains constant at any position due to the principal conservation of energy. At point A, the initial kinetic energy is zero due to zero speed, while the gravitational potential energy is maximized. As the pendulum swings from point A to point B, its height decreases, resulting in a decrease in gravitational potential energy. This gravitational potential energy is transferred to kinetic energy, causing an increase in speed. At point B, the kinetic energy and speed is maximized, due to greatest speed, while the gravitational potential energy is minimized due to the lowest point of the swing. As the pendulum swings from point B to point C, its speed decreases from the maximum to zero, leading to a decrease in kinetic energy to zero. This kinetic energy is transferred to gravitational potential energy. To find the maximum speed, v, that the mass reaches at the point B, we can apply the principle of conservation of energy. And assuming a decrease in height from point A to point B of 0.1 meters, the decrease in gravitational potential energy is equal to the increase in kinetic energy. Using the equation mgh equals half of m times v squared, we can substitute the values in m equals 0.6, g equals 9.8, and h equals 0.1. Solving this equation, we find that the speed, v, equals 1.4 meters per second. If air resistance is present, the speed at which it reaches the point B will be less than 1.4 meters per second, because some energy is lost to thermal energy due to air resistance. In another scenario, let's consider a ball with a mass of 1.5 kilograms rolling downward at rest from a height of 2 meters to a height of 0.5 meters along the given path as shown. We assume there are thermal energy losses due to friction of 5 joules at the final speed v. To find the final speed, v, we can apply the principle of conservation of energy. The decrease in gravitational potential energy is equal to the increase in both kinetic energy and thermal energy. Using the equation mgh equals half of m times v squared plus thermal energy lost, we can substitute the values in m equals 1.5, g equals 9.8, h equals 2, minus 0.5, and thermal energy lost equals 5. Solving this equation, we find that the speed, v, equals 4.8 meters per second. If air resistance and friction is ignored, the speed, v, will be greater than 4.8 meters per second, because there will be no thermal energy lost due to air resistance. Power. Power is defined as the work done, or energy transferred per unit time. Its unit is measured in joules per second, or watt, W. Power is the scalar quantity, representing only magnitude. The equation of power can be expressed as P equals W divided by T, or E divided by T, where P is the power in watts, W is the work done in joules, T is the time in seconds, and E is the energy in joules. Experiment to investigate your power output. First, measure your mass using a scale balance, and then multiply by gravity to get your weight in newtons. Second, measure the height of one step of the stairs in meters. Third, count the number of steps. So, the total height of stairs equals n/d meters. Fourth, time how long to climb the stairs is seconds using a stopwatch. Work done climbing the stairs equals force times distance. Force is your weight and distance is the height of stairs. So, work done is W times N times D. Power equals work done over time taken. So, power is W, N, T, over T. Efficiency is defined as the ratio of the useful energy, or work or power output from the system to its total energy, or work or power input. Efficiency can be expressed as the decimal, fraction, or percentage. Here are the efficiency value for different devices or bodies. Light bulb. The electrical energy input is 120 joules. The useful output energy is light of 50 joules. And the waste output energy is thermal of 70 joules. Therefore, the efficiency of light bulb is 50 divided by 120 is equal to 0.417, or 41.7%. Television. The electrical energy input is 550 joules. The useful output energy consists of 220 joules for light and 250 joules for sound. The waste output energy of 80 joules for thermal. Therefore, the efficiency of television is 470 divided by 550 is equal to 0.855 equals 85.5%. Electric motor. The electrical energy input is 750 joules. The useful output energy is 450 joules for kinetic energy. The waste output energy consists of 200 joules for sound and 100 joules for thermal energy. Therefore, the efficiency of electric motor is 450 divided by 750 is equal to 0.6 equals 60%. Running person. The chemical potential energy input is 800 joules. The useful output energy is 500 joules for kinetic energy. The waste output energy is 300 joules for thermal energy. Therefore, the efficiency is 500 divided by 800 is equal to 0.625, or 62.5%. Sankey diagrams can be used to represent energy transfers. These diagrams are characterized by the splitting arrows that show the proportions of the energy transfers taking place. The different parts of the arrow in a Sankey diagram represent the different energy transfers. The width of each arrow is proportional to the amount of energy being transferred. The left-hand side of the arrow represents the energy transferred into the system. The straight arrow pointing to the right represents the useful energy output. The arrow that bends away represents the wasted energy. This is a result of the conservation of energy, where the total energy input is equal to the total energy output, which is the sum of the useful energy output and wasted energy output. Therefore, the length of L1 equals L2 plus L3 plus L4. For example, let's draw a Sankey diagram for the electric motor with the electrical energy input is 1000 joules. The energy output as kinetic energy of 600 joules, thermal energy of 300 joules, and sound energy of 100 joules. We will set up the scale, where one division represents 100 joules. The width of the energy input arrow will be 10 divisions, equivalent to 1000 joules. The width of the straight arrow pointing to right, representing the useful energy output for kinetic energy, will be 6 divisions, equivalent to 600 joules. The width of the arrow that bends away, representing the thermal energy, will be 3 divisions, equivalent to 300 joules. The width of the arrow that bends away, representing the sound energy, will be 1 division, equivalent to 100 joules. To calculate the efficiency of the motor, we divide 600 by 1000 equals 0.6, or 60% efficiency. Candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. Energy resources are large stores of energy that can be used to generate electricity and heat homes and businesses. Some electricity drawn from the national grid is generated from non-renewable resources, and some is generated from renewable resources. Non-renewable energy resources are natural resources that cannot be replaced by nature as quickly as they are being used. Examples of non-renewable energy resources include fossil fuels such as coal, oil, and natural gas. These fuels contain chemical potential energy derived from the sun. Nuclear fuel, such as uranium and plutonium, contain nuclear energy. Renewable energy resources are nature resources that can be repeatedly and does not run out, because it can be replaced by nature at faster rate than they are being used. Examples of renewable energy resources include biofuel or biomass is the waste of living things, which contains chemical potential energy derived from the sun during photosynthesis. Some biomass, such as wood from trees, food corp residues, and animal waste. Geothermal energy is the thermal energy found beneath the Earth's surface. Wind energy, which contains the kinetic energy derived from the sun. Hydroelectric energy, which contains the gravitational potential energy derived from the sun. Tidal energy, which contains the gravitational potential energy created by the moon. Wave energy, which contains the kinetic energy derived from the sun. Solar energy is light energy from the sun. Fossil fuel power plant. Fossil fuels such as coal, oil, and natural gas are burned to boil water, producing steam. This changes the chemical potential energy in fossil fuels to thermal energy, which is stored in the steam. The high-pressure steam passes through turbines and forces them to spin. This changes the thermal energy to kinetic energy, which is stored in the turbines. The turbines are connected to a generator, which causes the generator to spin and generate electricity. This changes kinetic energy to electrical energy. This electrical energy is transferred through the national grid to homes or industrial factories. The water steam that passed through the turbines is sent to cooling towers and returns to the boiler again. Here are some of the advantages of fossil fuel power plants. Reliable energy resource. Fossil fuel power plant can produce electricity at any time, regardless of the weather. Produces large amounts of energy at fairly short notice. Fossil fuel power plants can produce large amounts of electricity quickly, which is helpful during times of peak demand. Scalable. Fossil fuel power plants can be scaled up or down to meet changing energy demands. Here are some of the disadvantages of the fossil fuel power plants. Non-renewable energy resource. Fossil fuels are a finite resource that will eventually run out. Produces air pollution. Fossil fuel power plants emit harmful pollutants into the air, which can contribute to climate change or greenhouse effect and other environmental problems. The cost of fuels affects the price of electricity. The price of fossil fuels can fluctuate, which can affect the price of electricity generated by fossil fuel power plants. Nuclear power plant. The nuclear fuels such as uranium or plutonium in the nuclear reactor will releases the thermal energy due to nuclear fission. This converts nuclear energy to the thermal energy. This thermal energy used to boil the water, producing steam. So the thermal is stored in the steam. The high-pressure steam passed through the turbines and forces them to spin. This converts the thermal energy to kinetic energy, which is stored in the turbines. The turbines are connected to a generator, which causes the generator to spin and producing electrical energy. This converts kinetic energy to electrical energy. This electrical energy is transferred through the national grid to homes or industrial factories. The water steam that passed through the turbines is sent to cooling condenser and returns to the boiler again. Here are some of the advantages of nuclear fuel power plants. Reliable energy resource. Nuclear fuel power plant can produce electricity at any time, regardless of the weather. Large amount of energy is produced from a small amount of fuel. Scalable. Nuclear fuel power plants can be scaled up or down to meet changing energy demands. No greenhouse gas emissions. Nuclear power plants do not produce greenhouse gases or other pollutants. Here are some of the disadvantages of the nuclear fuel power plants. Non-renewable resource. Nuclear fuels are a finite resource that will eventually run out. Waste disposal. Nuclear waste is radioactive and must be disposed of carefully, which can be a high costly and difficult process. High cost to build. Nuclear power plants are very expensive to build, which can make them a less attractive option than other forms of energy. Safety concerns. Nuclear power plants pose a risk of accidents, which can have catastrophic consequences. Biofuel or biomass power plant. Biomass, such as woods or cork residues, are burned to boil water, producing steam. This converts chemical potential energy of biomass into thermal energy, which is stored in the steam. The high-pressure steam passes through turbines and forces them to spin. This converts the thermal energy to kinetic energy, which is then stored in the turbines. The turbines are connected to a generator, which causes the generator to spin and generate electricity. This converts kinetic energy to electrical energy. This electrical energy is transferred through the national grid to homes or industrial factories. The water steam that passed through the turbines is sent to cooling condenser and returns to the boiler again. Here are some of the advantages of biomass power plants. Renewable energy resources. Biomass are an infinite resource that will never run out. Less garbage in landfills. Biomass power plants can help to reduce the amount of garbage that goes into landfills. Carbon neutral. Biomass is carbon neutral, meaning that the carbon dioxide produced when the fuel is burned is balanced by the carbon dioxide absorbed when the biomass is grown. Here are some of the disadvantages of the nuclear fuel power plants. Can take a lot of land. Biomass power plants can require a lot of land to grow crops or harvest wood. Not entirely clean. Biomass power plants can still produce some emissions, such as nitrogen oxides and sulfur dioxide. Geothermal power plant. Water is pumped into shafts below the Earth's surface. Water is heated by the hot rocks and returned via another shafts as steam. The thermal energy is transferred from the Earth to the water steam. The high-pressure steam passes through turbines and forces them to spin. This converts the thermal energy to kinetic energy, which is stored in the turbines. The turbines are connected to a generator, which causes the generator to spin and generate electricity. This converts kinetic energy to electrical energy. This electrical energy is transferred through the national grid to homes or industrial factories. The water steam that passed through the turbines is sent to cooling towers and returns to the Earth's surface again. Here are some of the advantages of geothermal power plants. Renewable energy resources. Geothermal energy is an infinite resource that will never run out. Reliable energy resource. Geothermal power plants can produce electricity at any time, regardless of the weather. Here are some of the disadvantages of the geothermal power plants. Few suitable locations. Geothermal power plants can only be built in areas where there is hot rocks lie quite near to the surface. This is possible in volcanic areas. High cost to build. Geothermal power plants are very expensive to build. Can result in the release greenhouse gases from underground. Waves power plants. High-speed waves pass through the chamber wall and compressing air column. This transfers the kinetic energy of the waves to the air particles. The air particles pass through the turbines, forcing them to spin. This transfers the kinetic energy of the air particles to the turbines. The turbines are connected to a generator, which causes the generator to spin and generate electricity. This converts the kinetic energy to electrical energy. This electrical energy is then transferred through the national grid to homes or businesses. Here are some of the advantages of waves power plants. Renewable energy resources. Waves energy is an infinite resource that will never run out. No greenhouse gas emissions. Waves power plants do not produce greenhouse gases or other pollutants. Here are some of the disadvantages of the waves power plants. Few suitable locations. Waves power plants can only be built in areas where there is waves energy. Not reliable. Wave power is not always available, it depends on the weather. Waves are generated by wind, so if there is no wind, there will be no waves. Tidal power plants. Tides occur twice a day due to the gravitational attraction force between the Earth and the Moon. The water at high tide level flows to the low tide level. This converts the gravitational potential energy of the water into kinetic energy of the water. This high-speed water passes through turbines. This transfers the kinetic energy of the water to the kinetic energy of the turbines. The turbines are connected to a generator, which causes the generator to spin and generate electricity. This converts the kinetic energy into electrical energy. This electrical energy is then transmitted through the national grid to homes or businesses. Here are some of the advantages of tidal power plants. Renewable energy resources. Tidal energy is an infinite resource that will never run out. No greenhouse gas emissions. Tidal power plants do not produce greenhouse gases or other pollutants. The tides are very predictable. The amount of energy can be produced at regular intervals. Here are some of the disadvantages of the tidal power plants. Few suitable locations. Tidal power plants can only be built in areas where there are strong tides, where the ocean is narrow and the coastline is indented. Not reliable. Tidal power is not always available. Environmental impact. Tidal power plants can have a negative impact on marine life, such as disrupting fish migration patterns and disrupt shipping. Hydroelectric power plants. The water is stored at a dam, and then it falls from the high level to the lower level. This converts the gravitational potential energy of the water into kinetic energy of the water. The high-speed water passes through turbines. This transfers the kinetic energy of the water to the kinetic energy of the turbines. The turbines are connected to a generator, which causes the generator to spin and generate electricity. This converts the kinetic energy into electrical energy. This electrical energy is then transmitted through the national grid to homes or businesses. Here are some of the advantages of hydroelectric power plants. Renewable energy resources. Hydroelectric power is an infinite resource that will never run out. No greenhouse gas emissions. Hydroelectric power plants do not produce greenhouse gases or other pollutants. Reliable. Hydroelectric power plants can produce electricity at any time, regardless of the weather, and large amount of energy at short notice. Scalable. Hydroelectric power plants can be scaled up or down to meet changing energy demands. Here are some of the disadvantages of hydroelectric power plants. Few suitable locations. Hydroelectric power plant usually requires the flooding of valley by building a big dam. Environmental impacts. The construction of hydroelectric power plants can have a significant environmental impact, such as flooding and habitat destruction. Economic impacts. The construction of hydroelectric power plants can be expensive. Wind power plants. Strong wind passes through the turbines, forcing them to spin. The kinetic energy of air particles is transferred to the turbines. The turbines are connected to a generator, which causes the generator to spin and generate electricity. This converts the kinetic energy to electrical energy. This electrical energy is then transmitted through the national grid to homes or businesses. Here are some of the advantages of wind power plants. Renewable energy resources. Wind power is an infinite resource that will never run out. No greenhouse gas emissions. Wind power plants do not produce greenhouse gases or other pollutants. Here are some of the disadvantages of the wind power plants. Few suitable locations. Wind power plants can only be built in areas where there are strong wind. Noise. Wind turbines can produce noise, which can be a nuisance for people who live nearby. Not reliable. Wind power is not always available, it depends on the weather due to wind speeds must be sufficient. Can have a visual impact. Solar power plants. Light energy shine on the solar cell, producing the electrical energy. This converts the light energy into electrical energy. The electrical energy is then transmitted through the national grid to homes or businesses. Here are some of the advantages of solar power plants. Renewable energy resources. Solar power is an infinite resource that will never run out. No greenhouse gas emissions. Solar power plants do not produce greenhouse gases or other pollutants. Here are some of the disadvantages of the solar power plants. Few suitable locations. Solar power plants can only be built in areas where there is strong sunlight. Large area needed to produce a large amount of the energy. Not reliable. Solar power is not always available, it depends on the weather, and only works when sunny. Solar panels. Solar panels can be used to heat water or air for heating in a house. Heated water for domestic use, such as showering, bathing, and washing dishes. Sunlight shines directly on the solar panels. A glass sheet is coated with a substance that reduces the reflection of sunlight. Glass sheet traps hot air. This air is heated by sunlight and then transfers that heat to the water in pipes by conduction. A blackened metal surface is a good absorber and conductor of heat. It collects sunlight and transfers it to heat, then heating the water in pipes by conduction. Copper pipes are good conductors. They collect sunlight and transfer that heat to the water in pipes by conduction. The insulating material reduces heat loss from the water in pipes. The heated water then flows through pipes to the rest of the house. Candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. Pressure. Pressure is defined as a force per unit area. We can write the equation of the pressure as P equals F is divided by A, where P is the pressure in Newton per meter squared or Pascal. F is a force in Newton. A is the area in meter squared. Pressure of a solid object on the contact surface area. A cuboid solid has dimensions as 3 meters, 2 meters, and 5 meters. It laying on the contact surface, and its weight of 500 newtons exerts on the contact surface area of 3 meters by 2 meters. The contact surface area is 3 times 2, which it equals 6 meters squared. The force is the weight of the cuboid. The pressure can calculated using force divided by area. So, the pressure is 500 divided by 6, which it equals 83 Pascal. The same cuboid solid is laying on the contact surface. Its weight of 500 newtons exerts on the contact surface area of 3 meters by 5 meters. The contact surface area is 3 times 5, which it equals 15 meters squared. So, the pressure is 500 divided by 15, which it equals 33 Pascal. The same cuboid solid is laying on the contact surface, and its weight of 500 newtons exerts on the contact surface area of 2 meters by 5 meters. The contact surface area is 2 times 5, which it equals 10 meters squared. So, the pressure is 500 divided by 10, which it equals 50 Pascal. We can conclude the minimum pressure is 33 pascals, when the largest contact area, while force remains the same. And the maximum pressure is 83 pascals, when the smallest contact area, while force remains the same. From this information, we can conclude that the pressure increases as the contact area decreases while the force remains the same. In the opposite way, the pressure increases as the force increases while the contact area remains the same. An application of pressure in everyday life. When large pressure is due to the small area. For example, the spikes on soccer shoes reduce the area of contact. This increases the pressure, providing the soccer players with a better grip on the ground. Knives, scissors and saws are all used to cut objects, because they have sharp edges that create a small area of contact, resulting in high pressure that helps to cut the objects easier. The shovel's sharp edge creates a small area of contact with the ground, resulting in a high pressure that helps to dig the soil easier. When small pressure is due to the large area. For example, a wooden plank increases the surface area of contact with the soft ground, which reduces the pressure and prevent the wheelbarrow from sinking on the soft ground. The wider shoulder pad has a large area, which reduces the pressure that acts on the shoulder. The elephant and the polar bear have big feet, which creates a large surface area of contact with the soft ground or snow. This reduces the pressure, so they do not sink too deeply. Pressure in a liquid. Pressure in a liquid acts on an object in all directions. The pressure is higher at the greater depths in the liquid, resulting in a higher force acting on an object compared to shallower depths. Pressure decreases as the object rises through the liquid. The equation of pressure in a liquid is P equals rho g h, where P is pressure in newtons per meter squared or pascals. Rho is the density in kilograms per cubic meter. G is the acceleration due to gravity, equal to 9.8 meters per second squared. H is the depth in meters. We can conclude from this equation that the pressure in a liquid depends on the density of a liquid and the depth in a liquid. We can prove this formula. If the container is filled with a liquid, the pressure in the liquid at the bottom of the tank is the force divided by the base area. The force is the weight of a liquid, which is equal to the mass of the liquid multiplied by gravity. The mass of the liquid is density of liquid multiplied by the volume of the container. The volume of the container is equal the depth multiplied by the base area. So, the pressure at the bottom is equal to F over A. By substituting the force, F, with W equals mg. Substituting the mass, m, with rho v. And substituting the volume, v, with h, a. We can derive the equation P equals rho g h. The pressure in a liquid depends on the density of a liquid and the depth in a liquid. Consider two containers filled the same liquid and having the same depth. The pressure at the bottom of the liquid in both containers is the same because the liquid has the same density and depth. It is not affected by the size of the containers. The container has three holes labeled as A, B, and C, which cause the liquid to flow out of the container. The liquid flows out of the container at point C further than B and A because point C experiences a higher pressure due to its greater depth. Conversely, the liquid flows out from point A over the shortest distance because point A is shallower and has the lowest pressure. A barometer is a device used to measure atmospheric, or air, pressure. A simple barometer was made by filling a long glass tube with mercury and then inverting it into a bowl of mercury. The mercury falls until the weight of the column is supported by the air pressure pushing down on the mercury in the bowl as shown. This creates a vacuum at the top of the tube, which has zero pressure. As a result, the air pressure outside the tube acts on the mercury surface, pushing it up the tube to a height that balances the weight of the mercury column. So, the air pressure acts on the surface of mercury to equal the mercury pressure in the column at the same level. If the column of mercury is 0.74 meters high, what is the air pressure? The density of mercury is 13,600 kg per cubic meters. Take the gravitational field strength as 9.8 Newton per kilogram. The air pressure is equal to rho g h. To substitute rho equals 13,600, g equals 9.8, and h equals 0.74. So, P equals 98,600 pascals. Air particles at the top of the tube reduce the mercury column height, causing the barometer to underestimate the true air pressure. I hope you found this video helpful. If you did, I would be grateful if you would subscribe, share, like and leave a positive comment. Your support will encourage me to create more content. Thank you.